So, picture this scenario. A team of really veteran engineers writes this mathematically perfect line of code.
Right.
And it's beautiful, it's totally symmetrical, logically sound. They push execute, and instantly the silicon just dies. The board goes completely black.
Just a complete catastrophic hardware panic.
Exactly. And I mean, for most people, a dead board is a disaster, right? It triggers this huge panicked rewrite. But today, in this deep dive, we are going to look at why that catastrophic failure was exactly what this team wanted.
Yeah, welcome to the deep dive. And if you are stepping into the arena of hardware engineering as a student, you probably already know that software simulations can lie to you.
Oh, they lie all the time.
They really do. Code that compiles cleanly on your laptop will just routinely fail in the physical world.
Right.
So today we are unpacking the very first significant failure of a custom unit test gate. The team called it the Anvil.
The Anvil, I love that name.
It's fitting, right?
Yeah.
And by breaking down the exact anatomy of how and why this failure occurred on a microscopic level, we're going to extract the 3 essential rules for safer hardware design verification cycles.
So I want to start by challenging a fundamental assumption we make when we write code. Because I look at the source material and I see these highly experienced developers falling into a trap that, seems obvious only in hindsight.
Hindsight is always 20/20.
Exactly. So my question to kick this off is, why is it that in engineering, the code you'd happily bet your entire career on, the code that looks the most intuitive and symmetric, is almost always the hidden landmine that brings the whole system down?
Well, it really comes down to a fundamental conflict between biological optimization and mechanical literalism.
Wait, biological optimization, like our brains?
Yeah, exactly. Our brains are hardwired to seek out and trust patterns. When we encounter a pattern that has worked successfully in, say, 2 previous instances, our cognitive architecture actively discourages us from critically analyzing the 3rd instance.
Because it's trying to save energy.
Precisely. We experience a cognitive shortcut. The brain basically says, hey, this is a known symmetry. Processing it from scratch is just a waste of metabolic energy.
But a microchip obviously does not have a brain to take those shortcuts.
Right. A processor evaluates every single instruction as a completely isolated physical event. It's governed purely by logic gates, clock cycles, and exact register states.
So when we trust the pattern, we basically stop reading the documentation.
Yes. We trust our biological intuition instead of the physics of the silicon.
Trusting the pattern over the physics. That is actually the perfect framework for understanding the environment where this crash took place.
It really is.
Because the team in our source material was building this environment called the Anvil, and it was a testing gate specifically designed for embedded fourth words.
Right. 4th.
And if you are a student accustomed to writing in Python, C++i, or Rust, you might look at fourth and think it belongs in a museum, right? Why is a modern embedded hardware team using a language that was invented in the 1970s?
I mean, it's a fair question. But 4th is uniquely suited for the bare metal realities of embedded hardware. It is not just a language. It is an entire operating system, a compiler, and an interpreter all rolled into one incredibly tiny footprint.
So it's super lightweight.
Unbelievably lightweight. And in 4th, you don't write sprawling monolithic functions. You write words.
Words?
Yeah, a word is a tiny, highly specific command that does one thing. And you string these words together to create new words, building a dictionary from the ground up until you have a custom vocabulary explicitly designed for your hardware.
So the overhead is virtually non-existent.
Non-existent. You have direct, uncompromising access to the memory registers. But, that power comes with 0 safety nets.
So if you tell fourth to do something mathematically absurd,
it won't throw a polite compiler warning. It will execute the instruction and literally burn down the house.
Which is exactly why the Anvil was built. The development team instituted this brutal philosophy: a word that works in theory but breaks on real hardware does not get admitted to the language server.
It's a physical bouncer at the door of the code base.
Exactly. But couldn't they just write a strict linter script to catch these errors before they hit the chip? I mean, we have incredible static analysis tools today.
You'd think a linter would solve this, right?
Yeah, it seems way easier than routing everything through a physical test gate on the bench.
But static analysis fundamentally fails in 4th because of how the language operates at compile time. In 4th, a word can redefine the behavior of the compiler itself while the program is compiling.
Oh, wow. So it changes the rules while it's running.
Exactly. A linter cannot predict the state of the dictionary without essentially running the code. And more importantly, a linter is just another piece of software. It exists in this idealized mathematical vacuum.
Right.
Emulators and static analysis tools assume perfect conditions. They assume the memory responds instantaneously. They assume clock cycles are mathematically rigid.
But the physical world is messy.
Incredibly messy.
Yeah.
Real silicon suffers from things like parasitic capacitance.
Let's actually break that down for a second, because we throw terms like parasitic capacitance around a lot. What does that actually mean when the code hits the metal?
Okay, so whenever you have two conductive materials placed close to each other, separated by an insulator, you've created a capacitor.
Right.
Inside a microchip, you have billions of microscopic copper traces packed nanometers apart. Unintentionally, these traces act like tiny capacitors. They store electrical charge.
So they're soaking up energy they aren't supposed to.
Yes. When you try to send a rapid pulse of voltage down a trace to signal a binary one, that parasitic capacitance absorbs some of the charge. It literally rounds off the sharp edges of the electrical square wave.
Wow.
It introduces microscopic delays in signal propagation. An emulator knows absolutely nothing about the physical layout of the traces on your specific board. It doesn't simulate the voltage droop when a power-hungry peripheral turns on.
So testing on real silicon forces your code to survive the actual physics of the microchip.
Exactly. Complete with pipeline stalls, memory latency, and electrical noise. The silicon doesn't lie, because the silicon cannot ignore physics.
I feel like using a software emulator is like flying a multi-million-dollar flight simulator in a climate-controlled room.
Oh, that's a great analogy.
Yeah, I mean, it mathematically understands wind resistance, right? It is fantastic for learning where the instrumentation is. But testing your code on real silicon is like flying the actual physical plane through a thunderstorm.
Yes, exactly.
The simulator is going to completely miss the weird analog edge cases, like how the actual metal of the wings bends under real atmospheric pressure, or how a specific sensor physically shorts out when real rainwater hits the wiring harness.
That analogy holds up perfectly. The simulator knows the rules of the weather, but the plane experiences the reality of the storm.
Right.
When you adopt the Anvil mindset early in your engineering education, you undergo a necessary paradigm shift. You transition from a mindset of, I need to get this code to compile without errors.
Which is how we all start.
Right, to a much more cynical defensive posture. I need this code to survive the physical environment. You build a healthy paranoia. You stop trusting your theoretical assumptions, and you start demanding empirical proof from the hardware itself.
So we have this strict reality-based testing gate. Let's look at the first piece of code that stepped up to challenge it.
The bitfield trio.
Right, the bitfield trio. It was a block of code that looked flawlessly symmetric to operations the team had already proven. In hardware engineering, you are constantly manipulating specific bits within a register, right? To turn peripherals on and off or to read sensor flags.
It's the bread and butter of embedded work.
Exactly. And the team had successfully written two of these words. The first was BS bang, or bitfield set. The exclamation point in fourth denotes a store operation, so this word targets specific bits and forces them to 1.
And the second proven word was BFC bang, or bitfield clear. This word forces specific bits to 0. Both of these words were run through the Anvil, they manipulated the hardware perfectly, and the test gate admitted them to the codebase. They were proven assets.
Okay, so you have a mechanism to set bits and a mechanism to clear bits. The logical third piece of this puzzle is a mechanism to read or test those bits.
Right, you need to know if a specific flag currently reads as a 1 or a 0.
So the team created a new candidate word and named it BFAT. In fourth, the at symbol is the universal indicator for a fetch or read operation. So you have BFS bang, BFC bang, and BFAT. It looks like a perfectly matched set.
The symmetry is incredibly seductive.
It really is.
And that apparent symmetry is the exact trap that snared the developers. To understand the mechanics of the trap, we have to look really closely at how Forth manages data.
Let's do it.
Because if you are used to passing arguments into a function via parentheses like you would in C or Java, Forth is going to look completely backwards to you. Forth relies entirely on a data structure called a stack.
I want to be really careful here because a lot of textbooks compare a stack to like a pile of plates at a buffet.
Oh, I've always hated that metaphor.
Right. I hate it because it implies this sort of passive, gentle storage. When you are writing low-level hardware code, managing the stack is violent and highly volatile.
I completely agree. The buffet plate analogy is far too domestic for what is actually happening in the arithmetic logic unit.
So what's a better way to visualize it?
A much better way to visualize a last in first out, or LIFO stack, in embedded hardware is to think of a specialized tubular magazine on a shotgun.
Oh, I like that. That definitely raises the stakes.
You load rounds into the tube one by one. The last round you push into the tube is the only round you have immediate access to.
Right.
So if you loaded a slug and then you loaded buckshot on top of it, a buckshot is in the chamber. You cannot access the slug without physically ejecting the buckshot first.
Wow. Okay.
The sequence in which you load the data dictates exactly how the processor will consume it. We refer to the round currently in the chamber as the top of stack, or TOS.
That makes the reality of the architecture so much clearer. The position of these data items is literally the only way the processor knows what to do with them. It doesn't look for variable names, it just blindly pulls whatever is currently in the chamber.
Exactly. It's totally blind to context.
So how did the successful store operations, the set and clear words, manage this tubular magazine?
The source documentation shows that the set and clear words relied on what the team called a swap-first pattern.
A swap-first pattern, meaning the word takes the top two items in the magazine and mechanically flips their order before executing the core instruction.
Yes. In a typical bitfield operation, you need two pieces of data. You need the mask, which tells the system which specific bits you are targeting, and you need the address, which tells the system where in physical memory those bits live.
Right.
Let's say you push the mask into the stack first, and then you push the memory address. The address is now top of stack. It is in the chamber.
Okay, following so far.
But the underlying raw hardware instruction for storing data might require the mask to be in the chamber instead. So the word executes a swap command.
Ah, I see.
The processor physically shifts the register contents, pulling the mask to the top and pushing the address down one level. For the set and clear words, this swap-first pattern correctly aligned the data for the hardware store instructions. It was mathematically sound and verified on the silicon.
Okay, so the team sits down to write the third word, the fetch word. They look at the set and clear operations. They see the swap first pattern. They copy it.
Yep.
They assume the fetch operation will work exactly like the store operations, but they completely failed to account for what was actually sitting underneath their new word.
Underneath the fetch word was a core kernel word called bitat. This is the raw and native instruction inside the mecrisp kernel that executes the physical memory read.
And for context, mecrisp is a highly optimized bare metal fourth implementation built specifically for ARM Cortex microcontrollers, right?
Exactly. Its author, Matthias Koh, aggressively tuned the kernel to map fourth stack operations directly to ARM CPU registers. So the burning question the team failed to ask was, does the native bitat instruction share the same stack convention as the raw store instructions?
And the documentation proves it does not.
It absolutely does not.
The mecrisp kernel dictates that bitat expects the mask and the address, with the address sitting on top of the stack.
The kernel wants the address in the chamber.
So if I load the mask and then I load the address is top of stack.
Yeah.
The bitat command is looking at that and saying, perfect, the data is exactly where I need it, execute the fetch. But what did the team's new fetch word do?
It executed a swap.
Because they copied the symmetry of the store words.
Yes.
They took a perfectly aligned stack, ran a swap, and violently misaligned the variables. They pushed the address down, yanked the mask into the chamber, and then pulled the trigger on the bitat kernel word.
The sequence is fatal. They fed an upside-down stack directly into a highly optimized, unforgiving kernel instruction.
I have to pause here. I look at this scenario, and a part of me thinks, how does a team of professionals actually do this?
It sounds crazy.
If the stack conventions of a language like mecrisp are strictly documented, isn't this just sloppy engineering? It feels like reading the manual should be step one.
It is so easy to call it sloppy from the outside. But when you are neck deep in a code base, cognitive fatigue is a very real physical phenomenon.
That's true.
You are holding the architecture of hundreds of interconnected words in your working memory. When you see two words that behave identically and you are building the logical third sibling, your brain auto-completes the design pattern to save processing power.
So you don't even think to check.
You don't pause your workflow to cross-reference the mecrisp kernel documentation for the 1,000th time because your intuition is screaming that symmetry implies identical underlying mechanics.
It is the assumption that if the front door of a house swings inward, the back door must also swing inward. It's a shared design language.
But the hardware does not speak a design language. It speaks binary logic. This failure highlights why human code review is never a sufficient safety net in embedded systems. Another engineer reviewing that code would look at the swap and likely approve it, because their brain would fall for the exact same symmetrical illusion.
You cannot rely on human intuition to catch a violation of physics. You need the Anvil.
And the Anvil certainly delivered.
Oh, it did. The literal execution of this upside-down stack was catastrophic. I mean, in a high-level language like JavaScript, if you accidentally swap a string and an integer in a function call, the interpreter catches it, it throws a polite type error in your console, the program halts gracefully, and you go fix your code.
A very civilized process.
Right. But in embedded hardware, you are playing with live physical memory addresses. Let's look at the actual anatomy of this crash. What physically happened inside the silicon processor when it received this swapped stack?
We have to look at the mathematics of what the hardware attempted to compute, because the mask and the address were backwards. The source notes that the chip attempted to compute one shifted left by the address, instead of shifting one by the bit position.
Let's unpack the arithmetic there, because it is mathematically hilarious, but in a hardware context, it is terrifying. Normally, when you check a bit field, you are isolating a specific pin. You take the number 1 and you shift it to the left by a small mask value, say 3 or 5 or 12.
Right. Inside the arithmetic logic unit, the ALU of the processor, there is a physical component called a barrel shifter. It takes the binary representation of a number and physically moves the bits to the left or right across the registers.
Okay, so just moving bits over.
Exactly. If you take the binary number 0001 and shift it left by 3 positions, it becomes 10000. It is an incredibly fast single-cycle operation.
But because the team swapped the stack, the code didn't ask the barrel shifter to move the bit by 3 or 5 positions. It asked the ALU to shift the bit by the physical memory address.
Yes.
And in a modern 32-bit RM Cortex system, memory addresses are massive numbers. The base address for static RAM SRAM is often mapped to 0 by 200,000,000,000,000 in hexadecimal. In decimal, that is 536,870,912.
You are literally asking a 32-bit register to take a single binary digit and shift it to the left over 500 million times.
The scale of that error is just mind-blowing.
The ALU simply cannot execute that in any meaningful way. It shifts the bit entirely out of the register, usually resulting in a modulo wraparound that produces completely garbage data.
Okay, so it spits out garbage.
But generating a garbage integer isn't what crashed the chip. The fatal blow happened in the very next microsecond. The processor took that garbage data and tried to use it as a physical pointer to fetch data from memory.
It's like a delivery driver looking at a package. Instead of reading the label and driving to the house number, they try to physically pick up and shift the entire city block.
A fantastic visualization. And when the processor attempts to read from a completely chaotic, non-existent memory address, the physical architecture of the silicon intervenes.
How so?
Modern microcontrollers have a memory protection unit, or at the very least, a bus matrix that regulates traffic. When the processor issues a read command to an unaligned or reserved section of the memory map, the bus matrix immediately flags a violation. It pulls a physical hardware fault line low.
The chip literally throws up its hands and says, "This violates the laws of physics. Stop everything."
It triggers a hard fault handler. The silicon aborts the current instruction pipeline. It stops the program counter dead in its tracks. It violently overrides whatever the software was doing and jumps to a specific emergency address in the interrupt vector table.
Wow.
The normal execution of the board halts. The LEDs go dark. The communication ports drop. The silicon suffers a total panic.
So the Anvil operated exactly as designed. The test code crashed the chip before it could ever affect the main code base.
It did its job perfectly.
But now you're staring at a completely dead piece of silicon on your workbench. You don't have a helpful compiler error telling you what line of code failed. How do you even begin to perform an autopsy on a dead microchip? The source material details an incredible forensic process used to document this validation failure.
The dynamic of the debugging team here is one of my favorite details in the whole story. You have a 72-year-old electronics technician working alongside an AI to dissect the calltrace.
That is just such a cool image.
It is a brilliant collision of hard-earned analog intuition and hyper-modern pattern recognition.
Let's define the terms for the student listening. When a chip suffers a hard fault, what exactly is a calltrace and how do you extract it from a dead board?
A calltrace, or a stack dump, is basically the microchip's black box flight recorder. When the hard fault handler is triggered, The very first thing the core does before it completely locks up is push its current execution state onto the main stack.
So it writes down what it was doing before it dies.
Exactly. It saves the program counter, which tells you the exact memory address of the instruction it was trying to execute when it died. It saves the link register, which tells you what function called the bad instruction. And it saves the raw hexadecimal contents of the core CPU registers at the exact nanosecond of the crash.
Okay, so how do you get that data off the board?
Using a hardware debugger like an SWD or JTAG probe connected directly to the pins of the chip, you can suck that raw data out of the dead processor and look at it on your screen.
So you have a screen full of raw, unformatted hexadecimal numbers. This is where the team dynamic shines, right? I imagine the AI is incredibly fast at parsing that hex dump.
Unbelievably fast. Large language models are essentially vast pattern recognition engines. You feed it the raw register dump, and it instantly correlates the hexadecimal program counter against the compiled assembly map of the fourth dictionary. It points to the exact assembly instruction that caused the fault.
But the AI lacks physical context.
That's the catch. The AI doesn't know that the power supply on the bench has a slight ripple voltage, or that the specific revision of the silicon has a known errata regarding unaligned memory access.
Right.
That is what the 72-year-old technician brings to the table. Decades of watching how voltage behaves on an oscilloscope. The AI identifies the where, but the technician verifies the WHY by understanding the physical behavior of the board. Together they analyze the register dump and they find the smoking gun.
What exactly did the smoking gun look like?
The call trace explicitly named the kernel word bitat as the site of the crash. But the definitive proof was in the state of the processor's registers right as bitat was called.
Ah, the registers.
In the MechRISP architecture, the top of stack is often cached directly in a CPU register, usually R0 or R6 depending on the core. When they looked at the hex value sitting in that top of stack register, they didn't see a small mask value like 0 by 00008.
What did they see?
They saw a massive sweeping memory address like 0 by 2000008.
Boom, the physical proof. The call trace proved that the variables were loaded into the chamber backwards right at the moment of impact. The assumed symmetry of the fetch code had forced an address into the mask register.
It is the ultimate empirical reality check. You can argue with a linter. You can argue with a senior developer during a code review. You cannot argue with a register dump pulled from a crashed chip. It shows you exactly what you commanded the physical electrons to do.
The team finds the smoking gun. They realize the swap first pattern was a fatal assumption. They open their editor, they delete the swap instruction so the address stays safely on top of the stack exactly where the bitat kernel word wants it, and they save the file.
The bug is fixed.
The logic is sound. You would think the story ends here with a triumphant push to the main branch, but the Anvil was hiding a flaw of its own.
This specific twist is what elevates the entire narrative from a simple debugging tutorial into a masterclass on tooling and system trust.
I love this part.
The developers feed the corrected, mathematically perfect code back into the Anvil for validation, and the Anvil rejects it.
It rejected the fixed code? Did it trigger another hard fault on the chip?
No, the code never even made it to the silicon. The Anvil rejected it before it was compiled.
Wait, really? Why?
The gate's own internal software validator, the pre-flight script that checks the syntax of the code before it flashes the hardware, banned the submission for a completely arbitrary reason. The validator script was configured to reject any word name that contained the @ character.
The @ character. We just established that in Forth, the @ symbol isn't just common, it is the fundamental semantic indicator for a fetch operation. It is the core vocabulary of the language.
Precisely. Forth does not use reserved keywords in the way Python uses def or Java uses class. Forth builds a dictionary, and punctuation is highly semantic.
Right.
You use bit @ to fetch a bit, c @ to fetch a character, h @ to fetch a half word, and an exclamation point to store data. The entire ecosystem relies on these symbols.
So how does a test gate built specifically for Forth end up banning the most common symbol in Forth? I can almost guarantee I know how this happened.
How do you think?
The developer who wrote the Anvil's validator script likely used a standard regular expression, or regex, to filter the incoming text. In Bash scripts or Python pipelines, the @ symbol is often used for decorators or array indicators, so standard alphanumeric regex filters automatically strip it out.
They just copy-pasted a standard filter.
Yeah, they copied a standard CI/CD pipeline script and completely forgot to adapt it to the unique dialect of the language they were actually compiling.
You are diagnosing the exact root cause. The test harness was accidentally far more restrictive than the environment it was designed to protect. The tool was fundamentally ignorant of the domain it was operating in.
That is so frustrating.
The team had to physically stop debugging the microchip, pivot, and spend time debugging their own test gate. They had to rewrite the regex parser in the Anvil to accept the at symbol.
Now, a lot of engineers would look at this and throw their hands up. They would say, this is why heavy testing architectures are a waste of time. The Anvil is just creating artificial friction. It's slowing us down with false positives.
A lot of people definitely feel that way.
Yeah, but the source material and the team treat this failure as a massive victory. Why is finding a bug in your own test harness a reason to celebrate?
Because it forces an honest audit of your entire verification philosophy. When you build a test gate, you are essentially building a black box of trust. If that black box only ever flashes a green pass light, human nature dictates that you will eventually stop trusting it.
You start to think it's broken.
Exactly. You will start to wonder if the gate is actually checking anything at all, or if it's just a rubber stamp. When a tool fails, it can fail in two ways. It can produce a false positive, where it allows malicious or broken code into the system, or it can produce a false negative, where it unjustly rejects perfectly good code.
The regex bug was a false negative. The Anvil blocked good code.
Exactly. And fixing a false negative on the bench is the crucible that prevents catastrophic false positives in production. When a real fourth word triggers a failure in the validator, and the team has to open the Anvil up and fix its internal logic, the system proves that it is active, responsive, and subject to the same rigorous scrutiny as the code it is policing.
It proves it's actually working.
It builds immense systemic trust. You know the Anvil's doing the hard work because you just had to bleed to get your code through it.
It is the difference between a professor who gives everyone an A and a professor who grades brutally but is willing to admit when their own rubric is flawed.
Oh, that's exactly it.
When the tough professor finally gives you an A, you know you earned it. You respect the system because the system is committed to empirical truth, not just blind, rigid authority.
If you're building verification tools for your hardware, you must strike a balance. You build the gate to be as strict as physical reality demands, but you must remain humble enough to alter the gate when physical reality proves your tooling is flawed. You fix the regex, you accept the at symbol, and your pipeline becomes permanently more robust.
We have dissected an incredible sequence of events. We saw how the false promise of visual symmetry led seasoned engineers to write a fatal stack operation. We traced the mathematical absurdity of shifting a bit by a 500 million adjust down to the microscopic hardware fault handlers that panicked the silicon.
It's been quite a journey.
We watched a 72-year-old technician and an AI perform an autopsy on a register dump to find the smoking gun. And we explored the philosophy of why a test tool debugging its own rigid regex rules ultimately strengthens system trust.
It's a textbook case study.
It really is. So now it is time to distill this chaos into a repeatable framework. Let's lay out the 3 essential rules for safe hardware design cycles, drawn directly from the Anvil's first major failure.
These 3 rules are not theoretical guidelines. They are laws of physics written in the blood of crashed prototypes. They should form the foundation of any verification system you construct. Rule number 1, symmetry is not proof.
Let's expand on that for the listener. Just because the set word worked flawlessly with a swap first pattern did not mean the fetch word would.
As an engineer, you must actively train your brain to ignore its bias for aesthetic symmetry in architecture. Symmetry in high-level software might indicate good design, but in low-level hardware, it often masks wildly different underlying mechanics.
So you have to read the manual.
You must read the exact stack convention of the specific kernel word you are calling. The Silicon documentation is your only source of truth. Never assume that a fetch operation handles memory the same way a store operation does. In the realm of embedded hardware, assumptions are a liability. Verification is mandatory.
Rule number 2, the tool that tests must not be more restrictive than the thing it tests.
This is the at symbol pitfall. When you author a continuous integration pipeline, a test script, or a validation gate like the Anvil, your tool must be fluent in the full native dialect of the language it is evaluating.
Otherwise, it's just blocking you for no reason.
If your test harness arbitrarily bans valid operations, names, or characters due to lazy regex filters, you are not improving the security of your code base. You are merely generating artificial friction. A verification gate must be a perfect, unclouded mirror of the compiler's actual capabilities.
And rule number 3, the definitive directive, the entire reason the Anvil was built in the first place.
Rule number 3, test on real silicon, every word, no exceptions.
Every word. No exceptions. Why can't we just trust the software emulator for the simple stuff?
Because emulators simulate logic, but silicon enforces physics. An emulator might have allowed that massive bit shift to wrap around silently and return a zero without throwing a hard fault. The physical hardware is the only environment that matters.
It's the only real truth.
A word that crashes the microchip on your workbench is not a failure. It is an absolute gift. You caught the fatal assumption in total isolation. You trapped the bug before it was committed to your repository, before it poisoned the language server, and months before it was permanently flashed into a medical device, an automotive braking system, or an aerospace flight controller. The silicon crash on the bench is the ultimate proof that your safety systems are functioning perfectly.
Let's bring this narrative to its final resolution. We have the rules, the gate is fixed, the stack alignment is understood. Frame the final evolution of this test gate for us.
The development team absorbed these lessons and rewrote the fetch operation. The final verified code was a masterclass in elegant reality. It simply read, bit swap, bit app.
Let's walk through the mechanics of that final command, instruction by instruction, to see how it aligns the physical stack. The system provides a bit number and a memory address.
Correct. The stack starts with the bit number and then the address. The first instruction, bit, is a helper word that takes the raw bit number and converts it into a binary mask. So the stack is now holding the mask and then the address.
And we know from the mecrisp documentation that the kernel word bitat absolutely requires the address to be the top of stack. It needs the address in the chamber.
So the team executes a swap. The processor pulls the address to the top and pushes the mask down. The stack is perfectly aligned to the exact physical requirements of the kernel. Finally, they execute bitat.
The word was submitted to the newly fixed Anvil. The regex parser allowed the at symbol. The compiler flashed the silicon, and the hardware executed the sequence.
It verified live on the bench. No bus matrix violations, no hard faults. It performed exactly as designed. If the targeted bit was set, the hardware returned a true value, represented as -1 1/4. If the bit was clear, it returned a 0.
The test passed.
The Anvil admitted the word and pushed it to the active language server. The bitfield trio set, clear, and test was finally complete, mathematically sound and empirically proven on the metal.
There is a profound poetry in the motto the team adopted after this ordeal. The source material notes, they said, the Anvil got hammered and it rang true.
I love that quote.
The very first failure of the gate was the exact trial by fire it required to prove its worth. It proved it could catch a lethal human assumption regarding symmetry, and it proved it was robust enough to reveal its own internal regex flaws. The system emerged vastly stronger because it survived the hammer blow of physical reality.
That is the highest aspiration of hardware engineering. You do not build systems with the arrogant assumption that your code will be perfect. You build systems that are relentlessly resilient enough to catch and isolate your inevitable imperfections.
As we conclude this deep dive, we've traced a remarkable path. We analyzed the deceptive comfort of visual symmetry, exploring how cognitive shortcuts lead to fatal stack misalignments. We journeyed into the arithmetic logic unit of a microchip to see how a bad memory pointer physically triggers a hardware panic.
From the macro assumption to the micro execution.
Exactly. We watched a veteran technician and an AI decode a hexadecimal call trace to locate the smoking gun. We saw a stubborn verification gate get debugged of its own restrictive regex rules, and we forged 3 unbreakable laws for hardware design. Symmetry is not proof. Testing tools must mirror reality, and you must demand proof from real silicon.
As you take these principles back to your own workbench, I want to leave you with a final consideration. The Anvil demonstrated unequivocally that only physical silicon can reveal the whole truth of an execution cycle. A software emulator would almost certainly have missed the specific memory bus panic that brought that chip down.
Which is a scary thought.
It is. When you look at the architecture of the modern world, the millions of lines of code governing the anti-lock brakes in your car, the routing switches in our power grids, the telemetry systems in our aircraft. How much of that code do you suspect has only ever been tested in the safe, idealized mathematical vacuum of a software simulator? As you prepare to engineer the next generation of embedded hardware, will you settle for the polite green check mark of an emulator, or will you demand that every line of your logic feels the heavy, unforgiving hammer of physical reality?
That is a brilliant and sobering question. It fundamentally changes how you perceive the invisible architecture running the world around us. Thank you for joining us on this deep dive. Keep questioning your assumptions, constantly check your stack conventions, and most importantly, keep testing on metal. We'll see you next time.